Okay, now homework problem here is to find the first derivative of y equals the inverse cos of sine of x in the domain of negative pi less than or equal to x less than or equal to pi. Okay, sorry, I was just interrupted. So find the first derivative of the function, the inverse cos of the sine of x in the domain from negative pi through to pi. Now we already know, I'm just going to draw a little sketch over here, that the inverse cos curve only applies, I've just drawn the inverse cos curve there. It's got a range of pi to 0, sorry, a range of 0 to pi and domain of 1 to negative 1. Now what I'm going to do here, I'm going to also sketch the sine curve. So here I've sketched the inverse cos curve, so y equals cos to the minus 1 of x. Here I'm going to sketch the curve y equals sine x, but I'm going to sketch this curve from negative pi through to pi, because they're saying to find the first derivative of this function in the domain negative pi to pi. So we know this sine curve is continuous and it goes on forever, so it's fine to do the domain of negative pi to pi for the sine curve. So I've just drawn my sine curve. This would be negative pi on 2, 0. We know that the amplitude is 1. Okay, now I'm going to do up a table of values. I think this would be the easiest way to do this question. So I'm going to go x. I'm going to go x values all the way from negative pi through to positive pi, going up by pi on 2. So I'm going to go if x is negative pi on 2, if x is 0, if x is pi on 2, and if x is pi. And I'm going to build this function y equals the inverse cos of sine of x. First, I'm just going to work out what the sine of x is. And I know that the sine of x is defined for all of these values here. So sine, if x is negative pi, so what's the sine of negative pi? It's 0. What's the sine of negative pi on 2? It's negative 1. What's the sine of 0? It's 0. What's the sine of pi on 2? Well, that's 1. And what's the sine of pi? Well, that's 0 as well. So now I'm going to keep building this. So I'm just sketching the curve because remember the first derivative is the gradient of the curve. So next thing I'm going to sketch is the inverse cos of the sine of x. So basically I want the inverse cos of these values up here. So what's the inverse cos of 0? Well, the inverse cos of 0 is pi on 2. Because cos to the minus 1 So the inverse cos of 0 is pi on 2. The inverse cos of negative 1 is pi. The inverse cos of 0 is pi on 2. The inverse cos of 1 is 0. And the inverse cos of 0 is pi on 2. So we've just come up with a number of points for the sketch of the inverse cos of all of these particular values of sine x. So I'm going to draw that curve now. And I'm going to draw the curve for x values ranging from negative pi through to pi. So when x is negative pi, the inverse cos of the sine of x is pi on 2. So I'm just going to make put pi on 2 here. So when x is negative pi, the inverse cos of just this first bit, the inverse cos of the sine of negative pi is pi on 2. So here, when x is negative pi on 2, the inverse cos of sine of x is pi. Now notice I've got a rise of pi on 2 and a run of pi on 2 here. So the gradient of this line is 1. When x is 0, the inverse cos of sine of 0 is pi and 2. Curve comes back down here. When x is pi and 2, the inverse cos of the sine of pi and 2 is 0, because we're getting 0 here. And when x is pi, the inverse cos of sine of pi is pi and 2, back up here. Now, if we look at the gradients of these lines, remember the first derivative is the gradient of the line. The gradient of this line, rise over run, you're rising pi and 2 and you're running pi and 2. So the gradient of this line is 1. Same with this one, rising pi and 2, running pi and 2, the gradient of that line is 1. And if we look at the gradient of this line, rising pi, running back pi, the gradient of that line is -1. So therefore, d by dx of inverse cos of x, inverse cos of the sine of x, is equal to, we'll do this -1 here, for values of x between -pi and 2, less than or equal to x less than or equal to pi and 2. Actually, I'm just going to put it as less than, because at that point, I'll just check. I'm just going to put less than because we've got a sharp point there and you can't actually differentiate at sharp points. So the derivative is -1 along here for values of x between -pi and 2 and pi and 2. And the derivative is, +1 for values of x from pi and 2 through to pi. Now I'm putting equal to pi because this line would normally just continue. So there's not going to be a sharp point here. This will actually continue and this will continue down here as well. So we've got the sharp points there. But if we did continue this along, there wouldn't be a sharp point here because it's just going to just keep going up and down like that. So, and then the derivative equals again 1 also for values of x from -pi less than or equal to x less than pi and 2. There will be no sharp point here at -pi, but there is a sharp point on the curve here at -pi. Sorry, -pi and 2. Okay, now, I know that some of you would have just done the derivative. I'll just show you another way. Some of you would have just done the derivative like this. If y equals the inverse cos of sine of x, then dy dx is using the rule. It's -1 over the square root of 1 minus sine of x squared times the derivative of sine x, which is cos x. But see, this will only give you the derivative for the values of for the domain to which cos to the -1 x applies. And if we draw the graph of cos to the -1 x, it only applies for the domain from -pi and 2 to pi and 2. So that's why if you do it this way, it will only give you the derivative from -pi and 2 to pi and 2. So and I'll just work that out. It's -1 over the square root of 1 minus sine squared x times cos x. Now 1 minus sine squared x is cos squared x, so it's -1 over the square root of cos squared x times cos x, which is -1 over cos x times cos x, which is just -1. But that domain, like I said, only will apply for where the inverse cosine function is defined, and that is only between -pi and 2 and pi and 2. So you wouldn't be able to do it for the other values. You'd only be able to do it for those values. So that's hence why we sketch the function. Okay. Now the other thing you can do is, if you don't want to read these values on the second line here, you can just go inverse cos of 0 on your calculator. Okay, and you can even just do that through drawing the cos function. We can see just by drawing the cos function, which is down here, that the inverse cos of 0 is pi and 2, and that the inverse cos of -1 is pi. and we know that this is the section of the cos curve that we use when we draw the inverse cos curve. The inverse cos of 0 again is pi on 2. The inverse cos of 1 is 0. And the inverse cos of 0 is pi on 2, which is where we got all these values from, all right, which helped us sketch the graph. Okay, that's it for question 9. Actually, what I also did was draw in Desmos the inverse cos of the sine of x, and you can see they wanted from the domain negative pi through to pi. Here's negative pi, roughly negative 3.1. See, the gradient of this line is positive 1. And that's up to negative pi and 2. Negative pi and 2 is negative 1.57. Then the gradient of the line from negative pi and 2 all the way through to here, which is pi and 2, because that's 1.57. Gradient of that line, sorry, this line gradient was positive 1. This line's gradient here is negative 1. Okay? And if we just continue, I'll just drag this, sorry, I'll just drag it across. And going from pi on 2, which is about 1.57, up to pi, which is 3.1, the gradient of this line here is positive 1. So just looking at the sketch also, we can see gradient of positive 1, and then negative 1, and then the gradient of positive 1. And if I make this whole curve smaller, you can just see that it just repeats and repeats and repeats. Okay, reason it goes like that is because there's no restriction in the domain for sine of x. Okay, question 10 here, which is to find the derivative of the inverse tan of x plus the inverse tan of 1 on x, and then to draw the graph. Okay, so let's differentiate. So inverse tan, derivative of inverse tan of x would be 1 over 1 plus x squared, and the derivative of inverse tan of 1 on x would be, well, that's going to be the derivative of the inverse tan of x to the negative 1. So it's going to be 1 over 1 plus 1 on x squared times the derivative of x to the negative 1. Now, remember, 1 on x is x to the negative 1. If you differentiate that, you bring the negative 1 to the front. So we get negative x, and we decrease this power here by 1. So times negative x to the power of negative 2. So that is 1 over 1 plus x squared plus 1 over 1 plus 1 on x squared times negative 1 on x squared, which is 1 over 1 plus x squared plus, I'm going to go common denominator here. Actually, I can do that, or I'm going to multiply numerator and denominator both by x squared, and I would get x squared over, now these both get multiplied by x squared, over x squared plus 1 times negative 1 over x squared. Now, remember, these two are together because this is the derivative of the inverse tan of 1 on x. And keep these in brackets together. And because of that, I can do some cancelling here with the x squared. So I've got 1 over 1 plus x squared plus, looks like, negative 1 over x squared plus 1. Well, this is just 1 over 1 plus x squared minus 1 over 1 plus x squared, which is 0. And so the derivative of this function is 0, which means that the gradient, remember, first derivative gives you the gradient of the function. So it's basically telling me that the gradient of this function is 0. In other words, the graph is flat. Okay, if the gradient's 0, the graph is flat. We just have to see where the graph goes now. And we can just do this by probably using a table of values. So now, second part of the question is to draw the graph of the inverse tan of x plus the inverse tan of 1 on x. So we'll do a table of values. Inverse tan of 1 on x plus inverse tan of x plus inverse tan of 1 on x. Obviously, x can't equal 0 because of this denominator here. So x cannot equal 0. So there's going to be some sort of discontinuity in the graph at x is 0. So let's just try some other values, okay? So let's try when x is 1, for example. Let's look. What's the inverse tan of 1? Tan of what is 1? Tan of pi on 4 is 1. And sorry, I need to write this out again. So we're looking at the inverse tan of x plus the inverse tan of 1 on x, okay? So when x equals 1, the inverse tan of 1 is pi on 4, and the inverse tan of 1 on 1, again, is pi on 4. So I should just do this all in one step. So when x is 1, and I will do it again, the inverse tan of 1 plus the inverse tan of 1 over 1 is pi on 4 plus pi on 4, which is pi on 2. So when x is 1, all right, we know that when x is 0, you've got undefined. When x is 1, we've got pi on 2. Okay? All right, I'm also going to look at when x is negative 1. So the inverse tan of negative 1 plus the inverse tan of 1 on negative 1, again, is just the inverse tan of negative 1. Now, tan of what? To get negative 1, you've got to be in quadrant 4. Remember, the inverse tan of negative 1, just from looking at properties, is the same as the negative inverse tan of 1 minus the inverse tan of 1. Which is, so we've got the inverse tan of negative 1 is the same as negative inverse tan of 1, and same with this one, negative inverse tan of 1, which is negative pi on 4 minus pi on 4. Well, that's negative pi on 2. So here's another point that we know about, is that when x is negative 1, that expression here equals negative pi on 2. So let's put that down there too. When x is negative 1, we've got negative pi on 2. Okay, now let's just now look at the derivative of the graph. We know that the derivative for this entire graph is 0. So therefore, the graph is flat. So it has to go like that. I mean, I can go in and try some other values on my calculator when x is 2. And if you do, the inverse tan of 2 plus the inverse tan of a half should also be pi on 2. But we know we don't need to do that because the gradient, when we did the first derivative, the gradient of the curve is 0. And we also know that x can't equal 0, so we have to have a big circle there. We also know that when x is negative 1, the y value is negative pi on 2. We also know that this graph has a gradient of 0 as well, so it's flat as well. And so there's obviously discontinuity here when x is 0. Okay, because the curve flat here for all values of x greater than 0, and for all values of x less than 0, the value of this expression in here is negative pi on 2. And so that's your curve sketch. Okay, we're now going to go on to another question. Looking at is this question 12. So a 6-meter long ladder is leaning up against a wall at a height of h and an angle theta. As shown, it says show that theta is the inverse sine of h on 6. Okay, I'm sure this isn't the bit that someone wanted help with. So we know that the sine of theta is h on 6. So theta is the inverse sine of h on 6. So that's very straightforward. And let's look at part B of the question. And that says the ladder slips down the wall at a constant rate of 0.05 meters per second. Now that's a dh dt, and because the ladder slips down the wall, this distance h will get smaller and smaller, so it's negative. So we'll say that dh dt is negative 0.05. So dh dt is negative 0.05 meters per second. Just going back to the question again. And it says find the rate at which the angle is changing in degrees and minutes. So we want d theta dt when the height is 2.5 meters. So the rate at which the angle is changing in degrees and minutes, when the height is 2.5 meters. Now this angle will get smaller as well. Okay. We want to find d theta dt when h equals 2.5 meters. Sorry, d theta dt. So we've got an expression here for theta. So theta equals the inverse sine of h on 6. So we can do d theta dh. And if you look at your rules, we're actually going to use the rule exactly as it stands because it's in that format of x on a. Okay, so it'll be 1 over the square root of 6 squared minus h squared. Okay, that's what dh d theta is. Sorry, you couldn't see that. So this is in the exact form of that. We know that if y equals inverse sine of x on a, then y dash or dy dx is 1 over the square root of a squared minus x squared. That's the form of the rule that we are going to use because our question is in that form. So remember, use the integral or the reverse of the integral that you see on your sheet if it's in that form. Okay, so that is 1 over the square root of 36 minus h squared. So therefore, d theta dt is going to be d theta dh times dh dt. Now let's just check out all the units that they're correct. Okay, and the ladder sits down the wall at 0.05 meters per second and the height is 2.5 meters. That looks fine. Okay, so d theta dh, and we have to substitute when h is 2.5, is 1 over the square root of 36 minus 2.5 squared times dh dt is negative 0.05, and we'll just work this out. 1 over the square root of 30 times negative 0.05, so we get negative 0.05 divided by the square root of 30. Now here, 36 minus 2.5 squared is 29.75, so it's 1 over the square root of 29.75 times negative 0.05, and the answer you get is negative 0.009166,984. Now we need to convert that into degrees and minutes. So we go on your calculator, shift DMS, and you get 0 degrees, minutes, seconds. 0 degrees, 0 minutes, 33 seconds. Okay, and it's negative. And the reason it's negative is because the angle is getting smaller. So it's getting smaller by 33 seconds in terms of the angular measure. So it's getting smaller by less than a degree every second, way less than a degree, much less than a degree. Let's just check this answer. Yes, it's 0 degrees, 0 minutes, 33 seconds per second. But this second here is angular measure. That 33 seconds is angular measure. This per second there is time measure. So it's 0 degrees, 0 minutes, 33 seconds per second. Okay, and it's negative because the angle, as the ladder slides down the wall, the ladder comes down, the angle gets smaller, and that's why we've got a negative value there. Okay.